Hello, fellow knowledge explorers and subscribers. Today we're diving into a fascinating topic in AI, the loss of plasticity in large language models, LLMs, and smaller language models, SLMs. Think of it like this. Imagine your brain getting stuck in a rut after learning the same things over and over, making it harder to pick up new skills. That's what happens to these AI models sometimes. Let's break it down in simple terms, step by step, and I'll include examples of the key algorithms mentioned to fix this issue. I'll explain any technical concepts using plain words instead of mathematical symbols or formulas, describing what they mean in everyday language. Plus, I've added extra details to each algorithm's description, including how they work under the hood, why they're effective, and real-world scenarios where they've been tested. What is loss of plasticity? During training, LLMs and SLMs can hit a wall where they stop learning new information effectively. This is called loss of plasticity. It's a big hurdle in neural network training because it stops the model from adapting to fresh tasks or changing data patterns. In short, the network forgets how to learn, like an old sponge that's too full to soak up more water. Early research pointed to problems like dead neurons, parts of the network that stop firing and become useless, or weights, the connections between neurons growing too large. But newer studies suggest the main culprit is non-stationary data. That's when the data keeps changing over time, like in real-world scenarios where information evolves. This triggers a chain reaction. Dead neurons, linearized, overly simplified units, and those oversized weights, all of which mess up the model's performance and make training unstable. Other factors play a role too, such as feature rank, how diverse and useful the model's internal representations are. It can drop, limiting what the model can handle. Sharpness of the loss landscape. The terrain the model navigates during training gets too jagged, making optimization tricky. Noise memorization. The model starts overfitting to random junk in the data instead of the real patterns. Fun fact, a recent study showed that dropout, a popular trick to prevent overfitting by randomly ignoring neurons during training, doesn't help with plasticity loss at all. Ways to fix it, algorithms and approaches. Based on research, experts have come up with several strategies to keep models plastic, adaptable. These fall into categories like regularizing parameters, architectural tweaks, adding noise, and reinitialization. I'll explain each category with real-world examples of algorithms, drawing from studies like the one referenced below. For each, I've expanded on the mechanics, how it operates step by step, its strengths and limitations, and practical applications to make it clearer. 1. Regularizing the parameters of the network. This means adding rules to keep the model's weights in check, preventing them from exploding or becoming unbalanced. It's like putting speed limits on a highway to avoid chaos, ensuring everything stays smooth and controlled. Example, L2 regularization, weight decay. How it works during training, this method adds a small penalty based on how large the weights have grown. Specifically, it considers the square of their sizes and nudges them smaller over time. This is often built right into common training tools like the adaptable optimizer, which adjusts the model's parameters gradually. Step by step, in each training update, the optimizer calculates the usual changes needed to improve the model, then subtracts a tiny fraction proportional to the current weight sizes to keep them from ballooning. Why it's effective? It promotes stability by encouraging balanced connections, which helps the model stay adaptable even after long training sessions. Without it, weights can spiral out of control, leading to dead spots in the network. Strengths and limitations. It's simple to implement and works well for preventing overfitting, but it might not fully solve plasticity loss in very deep networks where other issues like data shifts are dominant. Practical applications. In continual learning tasks, like training a model on a series of image recognition challenges, such as Permuted MNIST, where handwritten digits are rotated or altered in sequence, L2 regularization has been shown to extend the model's ability to learn new variations without forgetting old ones, improving overall accuracy by maintaining steady performance across tasks. 2. Architectural modifications. Change the model's structure or components to make it more resilient. Think of upgrading your car's engine for better long-distance performance, tweaking the design to handle wear and tear better. Example, reparameterized layer normalization. How it works? Layer normalization is a standard technique in models like transformers, the building blocks of LLMs, that helps stabilize training by adjusting the outputs of each layer to have consistent averages and spreads. However, in its basic form, it can cause certain scaling factors to shrink too much, blocking the flow of learning signals. Reparameterization fixes this by rewriting the normalization process in a slightly different way. It normalizes the data as usual, but adjusts the scaling and shifting steps to ensure the factors don't dwindle away. Step by step, for each batch of data, compute the average and spread, normalize the values, then apply a modified scaling, adding a constant like 1 to the factor before shifting. Why it's effective? This prevents the vanishing of important signals, keeping the network responsive to new data, and reducing the chain reaction that leads to dead neurons. Strengths and limitations. It's a low-cost change that boosts plasticity in transformer-based models, but it requires careful tuning and might not help in non-transformer architectures. In tests, it reduced performance drops in continual training by up to 10%. Practical applications. Envision transformers trained on datasets like CIFAR-100, which involves classifying 100 types of images, added incrementally over time. This modification has helped bridge the gap between training everything at once versus learning step by step, making it ideal for AI systems that need to evolve with new visual data, like self-driving car models updating on road scenes. 3. Adding parameter noise. Inject a bit of randomness into the weights to shake things up and prevent the model from getting too rigid. It's like adding some improvisation to a scripted play to keep it fresh, introducing controlled chaos to maintain flexibility. Example: shrink and perturb. How it works: this algorithm combines two actions periodically during training. First, it shrinks the weights by pulling them slightly towards zero using a regularization technique, similar to L2 but targeted. Then it adds random noise, small, normally distributed wiggles to the weights to introduce variety. Step by step, every few training updates, apply the shrinkage to dampen large values, calculate the noise based on a small variance, like a tiny fraction such as 1 in 100 million, and add it directly to the weights. Why it's effective? The shrinkage prevents weights from growing uncontrollably, while the noise reinvigorates stagnant parts of the network, mimicking natural variability and helping restore learning capacity. Strengths and limitations. It excels in maintaining even weight distributions across layers, avoiding sharp drops that cause instability, but tuning the noise level is crucial. Too much can disrupt training. In benchmarks, it often outperforms other methods in vision tasks. Practical applications. On CIFAR-100 with vision transformers, shrink and perturb has kept model accuracies near those of freshly retrained versions, making it useful for AI in dynamic environments like social media analysis, where data trends shift quickly. 4. Reinitialization techniques. Periodically reset parts of the model to restore its learning ability, mimicking how our brains prune and regrow connections. This is inspired by biology. Real neurons often ditch old synapses and sprout new ones at the same rate to stay adaptable. Example: continual backpropagation. How it works: this method identifies neurons that aren't pulling their weight, low utility ones, based on how much they contribute to the model's decisions, and resets them at a steady, very slow rate, like 1 in 10 million per update. It waits until neurons have matured through enough training cycles before considering them for reset. Step by step, monitor neuron activity over time, flag those below a utility threshold, and reinitialize them to random starting values once they've been active for a set period, e.g., thousands of training steps. Why it's effective? By refreshing underperforming parts, it clears out blockages and injects fresh potential, preventing the buildup of dead zones. Strengths and limitations. It shines in larger, fully connected networks but can struggle in smaller models or those using layer normalization, where resets might cause temporary dips. Practical applications. Tested on Permuted MNIST, 1,000 sequential twists on digit recognition, it's helped models handle long chains of tasks without losing steam, suitable for AI assistants that learn from ongoing user interactions. Example: redo, reset dormant units. How it works focuses on dormant neurons, those with extremely low activity levels below a set cutoff, like 5 in 10,000 of average activity. Every fixed number of updates, e.g. 128 steps, it scans the network, identifies these sleepers, and resets them to initial random values. Step by step, compute activity metrics during forward passes, compare to the threshold, and if low, wipe and restart the neuron's parameters. Why it's effective? It directly targets inactivity, which is a symptom of plasticity loss, restoring flow without overhauling the whole model. Strengths and limitations. Great for preventing shrinkage in multi-layer perceptrons, MLP blocks in transformers, but it can lead to training instability in deeper attention layers, causing some experiments to fail. Practical applications. In CIFAR-100 setups, Ray-Do has maintained adaptability in image models, making it handy for computer vision AI that processes evolving datasets like satellite imagery over time. Example: selective weight reinitialization. How it works: instead of resetting whole neurons, this targets individual weights connections. It measures each weight's usefulness by combining its size with how much it's changing during training, a utility score. Every set interval, e.g. 128 updates, it prunes the lowest scoring weights, those below a threshold, like 5 in 10,000 of the average score, and reinitializes them from their original random distribution. Step by step, during optimization, track these scores, sort and cut the bottom performers, then redraw new values for them. Why it's effective? It's more precise than unit-level resets, preserving good parts while refreshing the weak ones, which leads to better overall stability. Strengths and limitations. Highly modular and adaptable to any architecture, it works well in small networks and with normalization layers, but requires monitoring computational overhead. In studies, it beats unit-based methods consistently. Practical applications. On both Permuted MNIST and CIFAR-100 with vision transformers, it's enabled continual learning with minimal performance loss, ideal for edge AI devices like smart cameras that update models on the fly. Reinitialization is also key in dynamic sparse training algorithms, where the network prunes and regrows connections to stay efficient while saving computational resources. The downsides and upsides. Negatives: overdoing pre-training, training too long on initial data, can hurt fine-tuning on new tasks, as the model becomes too specialized and loses flexibility. Benefits: tackling plasticity loss enables continual learning, where models keep improving over time without forgetting old knowledge, like a lifelong learner absorbing endless books. This opens doors to more robust AI in fields like healthcare diagnostics or autonomous systems. Quick notes: reinitialization isn't just for plasticity, it's biologically inspired and used in sparse training to keep models lean and efficient. In the brain, neurons prune about 10 to 20% of connections periodically while growing new ones. AI is catching up to mimic this natural renewal process. There you have it, an even friendlier and more detailed take on this complex topic. If you have questions or want more on any part, just ask.